What if everything you've ever learned about the universe, every textbook, every documentary, every science class you've ever taken, only explains 4% of what actually exists? 4%. That's it. The stars, the planets, the galaxies, your body, the air you breathe, every atom that has ever been measured or studied by any scientist in human history, all of it combined makes up less than 5% of the total universe. The remaining 95 to 96%, we have no idea what it is. We can't see it, we can't touch it, we can't measure it directly. Scientists don't even know what to call it. Not matter, not energy, not particles. The most honest term they have is simply this: stuff, the stuff of the universe, and humanity is almost completely blind to it. That single fact should humble every human being who has ever claimed to understand reality. And yet, that's just the beginning. Because today, we're going on a journey into the deepest, most unsettling questions that modern physics still cannot answer. We're going to explore what happens when the universe literally tears itself apart at the quantum level. We're going to ask whether the future has already happened, and whether we're just actors in a movie that was filmed before we were born. We're going to investigate whether particles on opposite ends of the cosmos are secretly connected through dimensions we cannot see. We're going to question whether your mind, your consciousness, your deepest sense of self is fundamentally quantum in nature. And we're going to confront a question that has haunted philosophers and scientists alike for centuries. What happens to that consciousness when you die? Let's start at the end. Literally, the end of everything. There's a scenario in cosmology called the Big Rip. It's one of several hypotheses about how the universe might eventually meet its fate. And in this scenario, the expansion of the universe doesn't just continue, it accelerates. It accelerates so violently, so relentlessly, that eventually it begins to tear things apart. First galaxies, then solar systems, then planets, then the very molecules that make up those planets, then atoms, and finally, quarks. The most fundamental building blocks of matter we know of, ripped apart by the very fabric of expanding space itself. Now here's where it gets truly strange. Quarks have a peculiar property. They always exist in pairs or triplets, bound together by something called the strong nuclear force. And this force has a bizarre characteristic. The farther apart you try to pull two quarks, the stronger the force between them becomes. Imagine a rubber band that gets tighter and tighter the more you stretch it. And if you stretch it far enough, if you pump enough energy into separating those quarks, something remarkable happens. That energy itself becomes enough to generate a brand new quark. You never actually get an isolated quark floating alone, you just create more quarks. So here's the mind-bending question. If the Big Rip tears apart everything down to quarks, and tearing apart quarks generates new quarks, does that create a cascading infinite process? Could that process generate so much energy that it triggers another Big Bang? And if so, does that mean our universe is just one link in an infinite chain, emerging, existing, undergoing a Big Rip, spawning a new universe from the chaos and repeating forever? From the infinite past to the infinite future over and over again? It's a stunning idea, and for a while, it stumped some of the brightest minds in physics. But here's the key insight that cuts through the confusion. The Big Rip scenario requires a very specific type of dark energy called phantom energy, a form of dark energy with a strange negative quality to it. And if phantom energy is what's driving the Big Rip, then the rules change completely. When quarks are split apart under those conditions, they don't generate new quarks like they normally would. Instead, the phantom dark energy allows for the creation of negative energy particles, particles that, as far as we have ever observed, simply do not exist anywhere in the universe. So the cascading quark catastrophe that would trigger infinite Big Bangs? It doesn't happen because the very energy tearing things apart is also transforming what those things become when they're torn. But there's a deeper issue here. For the Big Rip to occur at all, phantom energy would have to be the dominant form of dark energy in our universe. And if that were true, we should be seeing negative energy particles popping into existence all around us. We should see wormholes, we should see white holes, we should see the kind of physics that would make things like the Alcubierre warp drive actually possible. But we don't see any of that. Not a single wormhole, not a single white hole. Not a single confirmed negative energy particle. Their complete absence suggests that phantom energy probably isn't what dark energy actually is. So then, what is dark energy? The honest answer is that nobody knows, and that admission, that simple statement of "I don't know," is one of the most important and powerful statements in all of science. But here's something remarkable that emerged recently. At the American Astronomical Society meeting, a gathering of professional astrophysicists from across North America, an organization with about 8,000 members, making each one literally 1 in a million among Earth's population, one of the final presentations was about the nature of dark energy. And what was presented genuinely shocked the scientific community. The Dark Energy Survey, which has gathered information about 15 million galaxies and their positions in the universe, appears to show something extraordinary. What we've been calling the cosmological constant, the value Einstein inserted into his equations to describe dark energy, probably isn't constant at all. It looks like it's actually changing over time. Think about what that means. Our assumption that the cosmological constant was constant comes directly from Einstein's equations of general relativity. If it's not constant, if it varies with the age of the universe, then Einstein's general relativity is missing something fundamental. The model we've relied on for over a century is incomplete. Now, before anyone celebrates catching Einstein in an error, remember, Einstein himself admitted the cosmological constant was a placeholder. He put it into his equations to make the math work when he believed the universe was static. He had no idea whether it represented anything physically real. And now, decades later, we're discovering that his mathematical placeholder might actually point to something profound, something real that we don't yet understand. The fact that dark energy appears to depend on time, to evolve as the universe ages, is further evidence that it represents something physical and not just mathematical convenience. But what exactly it is remains one of the greatest mysteries in science. 95% of what drives the expansion of the universe remains completely unknown to us. We can't even say whether it's matter or energy or something we haven't conceived of yet. And for anyone whose ego needs a check, we humans aren't even the majority of the stuff in the universe, not by a long shot. Now let's talk about something that has been haunting physicists for over a century. We have two extraordinary theories of how the universe works. General relativity, Einstein's masterwork, describes space and time and how they interact with matter and energy at the largest scales. Galaxies, black holes, the curvature of space-time itself. It works with stunning precision. And then we have quantum mechanics, the physics of the incredibly small, atoms, electrons, photons, quarks. It describes matter and energy at the tiniest scales, and it predicts experimental results with breathtaking accuracy. Here's the problem. These two theories don't get along. The mathematics of quantum physics breaks down when you try to apply it to space and time on cosmological scales, and the mathematics of general relativity falls apart when you try to apply it to subatomic particles. They're like two languages that each describe their own domain perfectly but cannot translate into each other. If you imagine a Venn diagram, one circle for general relativity, one for quantum mechanics, they don't overlap, they just barely touch, like two spheres kissing in the middle. There's no region where both theories work simultaneously. And here's what's fascinating. Light seems to sit right at the center of this divide. Light is fundamental to both theories. In relativity, the speed of light is the cosmic speed limit, the maximum velocity at which anything can travel through space and time, the very foundation of causality itself. In quantum mechanics, light is both a particle and a wave, energy that can transform into matter. Light seems to be the linchpin, the bridge waiting to be built between these two kingdoms of physics. But nobody has fully built that bridge yet. Some progress is being made. Researchers are exploring mathematical frameworks involving statistical physics and chaos theory, ways to take uncertain things and make them more certain. When these frameworks are pulled from the microscopic quantum world to the macroscopic relativistic world, they show promise of uniting both areas of physics. Historically, this is exactly how physics has always progressed. Somebody comes along with a new framework, a bigger circle that encloses both existing theories within it. That's exactly what Einstein did with Newtonian physics. He didn't throw Newton's laws away. He showed they were a special case within a larger, more complete framework. And someday, perhaps soon, someone will do the same with quantum mechanics and general relativity. Now let's venture somewhere truly mind-bending. In quantum physics, there's something called the path integral formulation. It calculates probabilities, not just for the path a particle actually takes, but for every conceivable path it could take through space and time. Then there's the two-state vector formalism, which describes quantum systems using both a state evolving forward from the past and a state evolving backward from the future. Both approaches suggest something extraordinary, that the mathematics of quantum mechanics works just as well running backwards as it does running forwards, and that raises a staggering question. Is time already complete? Think about this. Imagine the universe as a tall glass of water, where the bottom of the glass represents time zero, the Big Bang, and the water level rises as the universe ages. If we're sitting at the current surface of the water right now, has the glass already been filled to the top? Has every moment in time already occurred? Are we just experiencing a movie that was filmed long before we showed up to watch it? This idea is sometimes called a block universe or block time. In this model, there are 4 dimensions, 3 of space and 1 of time, and the entire block is already complete. Past, present, and future all exist simultaneously. We're just moving through them, experiencing each moment in sequence because our physical nature limits us to perceiving time in one direction. This concept has been explored brilliantly in fiction. Ted Chiang's Story of Your Life, adapted into the film Arrival, imagines what it would be like to perceive all of time at once, to see your entire life, beginning to end, not as a sequence, but as a complete picture. Kurt Vonnegut's Slaughterhouse-Five does something similar. The main character is granted access to his entire timeline, past, present, future, all accessible. It changes even how he speaks. He doesn't say, "When were you born?" because in a block universe, you are always being born. You're always dying. The timeline is simply filled out, complete, unchanging. But here's the scientific reality. The block universe is only one possible interpretation of the mathematics. No experiment has ever confirmed that the future already exists. The advanced concepts that support this idea, path integrals, retrocausality, two-state formalism, none have been proven experimentally. We simply don't know whether time is still being written or whether it's a finished book we're reading page by page. How would you even test such a thing? Some physicists have imagined experiments involving faster-than-light communication, perhaps using quantum entanglement between Earth and the Moon. If you could receive a response before light could have traveled the distance, it would suggest information can move outside normal space-time constraints, consistent with a block universe where future moments already exist. But such experiments remain far beyond current technology. For now, the true nature of time remains one of physics' most tantalizing unanswered questions. Speaking of quantum entanglement, let's explore one of the strangest phenomena in all of nature. Quantum entanglement is the process by which two particles become connected in such a way that measuring one instantly reveals information about the other, no matter how far apart they are. You could have one particle here on Earth and its entangled partner on the other side of the galaxy, and measuring one would instantly tell you about the other. This happens with no signal traveling between them, no force, no energy exchange. It just happens. Einstein famously called this spooky action at a distance, and it bothered him deeply because nothing, absolutely nothing, is supposed to communicate faster than light. That's a cornerstone of relativity, and yet entanglement produces instantaneous correlations across any distance. Here's a creative hypothesis some researchers have considered. What if entangled particles aren't actually distant from each other at all? What if they're right next to each other, but in a higher spatial dimension we cannot perceive? In our three-dimensional world, they appear to be light years apart, but in some fourth or fifth spatial dimension, they might be touching. The signal between them doesn't need to travel faster than light because it's not crossing three-dimensional space. It's taking a shortcut through a dimension we can't see. It's an elegant idea, Mathematically, it can work, but if you invoke an extra dimension to explain entanglement, you have to explain what that dimension is doing everywhere else in the universe. Is it affecting everything? Does every entangled pair use the same dimension, or different ones? The fundamental principle of quantum entanglement, as we currently understand it, is this. Once two particles are entangled and then separated, nothing physical connects them except their shared history. No wire, no field, no signal, no dimensional tunnel, just quantum information, mysteriously correlated across any distance. Recent experiments have measured the speed of entanglement formation at 232 attoseconds. That's 232 billionths of a billionth of a second. Incredibly fast, but still not providing clear answers about whether extra dimensions are involved. The deeper nature of entanglement remains unknown, and this echoes concepts from science fiction. Subspace in Star Trek, warp bubbles, layers of reality where normal physics doesn't apply. Star Trek, to its credit, has always tried to provide at least hand-wavy scientific explanations for its technologies. Star Wars, on the other hand, and this is said with love, is a space opera that cheerfully abandoned scientific rigor in favor of storytelling. The Force, hyperspace, midi-chlorians, entertaining, but not exactly physics. Now we arrive at perhaps the deepest, most personal question of all. Is consciousness the result of quantum physics? It's a question that seems almost designed to be unanswerable, because we don't truly understand either consciousness or quantum physics. We're asking one mystery to explain another. But that doesn't mean the question isn't worth exploring. In fact, it might be one of the most important questions we can ask. Think about free will, the sense that you are genuinely making choices, that your future isn't predetermined. The more neuroscience we do, studying how neurons fire, how brain chemistry works, how electrical signals propagate, the more it seems like the brain might be entirely deterministic, cause and effect all the way down. Every thought you have could just be neurons firing in patterns dictated by physics. But quantum mechanics introduces genuine uncertainty. At the quantum level, outcomes are probabilistic, not deterministic. You literally cannot predict with certainty what a particle will do next. And some researchers have wondered, what if that quantum uncertainty operates in our brains? What if the feeling of free will exists because there's genuine quantum randomness in our neural processes? Randomness that cannot be pinned down, cannot be predicted, even in principle. Nobel laureate Roger Penrose explored this idea decades ago. He proposed that consciousness might arise from quantum processes happening in tiny structures within neurons called microtubules. Quantum coherence in the spaces between our synapses giving rise to conscious experience. This isn't why Penrose won his Nobel Prize, he won that for black holes, but it shows how seriously brilliant minds take this question. But here's the fundamental problem. We haven't defined consciousness. Not really, not in any rigorous, scientific, testable way. Philosophers have debated this for millennia. Some argue everything is conscious to varying degrees, rocks, trees, insects, humans, just at vastly different levels. Others argue consciousness requires specific computational properties. There's no consensus. The best evidence that nobody truly understands consciousness? Look at how many books have been written trying to explain it. The consciousness section of any bookstore is enormous and ever-growing. Meanwhile, the section on gravity might have 2 books, because gravity is understood, consciousness is not. And here's something remarkable to consider. Your skin cells completely replace themselves every month or so. Much of your body's material has been replaced multiple times since you were a child. You probably don't have the same muscle cells you had a decade ago. Many of your atoms have cycled through, and yet your consciousness continues. It persists through all this physical change. It even grows, accumulating new experiences, new memories, new perspectives. How does your sense of self continue when the physical substrate keeps being replaced? That's one of the deepest unsolved questions in all of science and philosophy. This leads naturally to another question. Can consciousness be uploaded? Can you copy a mind? Science fiction has explored this extensively. In Altered Carbon, consciousness can be downloaded onto a small disk and transferred between bodies. The physical form is just a sleeve, interchangeable and disposable. The play Marjorie Prime imagines conversing with a deceased loved one through artificial intelligence, not truly them, but a convincing facsimile. But quantum physics suggests perfect uploading may be impossible. If consciousness depends on quantum states in the brain, those states cannot be perfectly copied. This is a fundamental principle called the no-cloning theorem. You cannot make an exact duplicate of an unknown quantum state. Every attempt destroys or changes the original information. So if consciousness is quantum, you could never create a perfect copy of someone's mind. Every transfer would produce variations, drift, subtle changes. The you that wakes up in a new body might not be you at all, just a convincing approximation that believes it's you. Even setting aside quantum effects, there's Heisenberg's uncertainty principle. You cannot simultaneously know both the position and momentum of every particle in your brain with perfect accuracy. Physics itself forbids complete knowledge of your own mental state. The dream of uploading consciousness to achieve immortality may be fundamentally impossible. All of this inevitably leads to the biggest question of all. Does consciousness survive death? Is there an afterlife? Before examining this scientifically, there's a profound philosophical consideration. Does believing in an afterlife rob us of the urgency of living now? If you truly understand that this moment, right now, is all you're guaranteed, you might live more fully, more presently, more intensely. But if you're always waiting for what comes next, always assuming there's something after, you might never fully inhabit the life you're living. From a scientific perspective, we know that once a person dies, their consciousness, whatever it was, goes silent. We can no longer communicate with it or detect it by any means we possess. More than a century ago, scientists actually X-rayed dying people, hoping to capture an image of the soul departing. It sounds absurd now, but at the time it was a reasonable experiment. Religion predicted a soul exists inside the body. X-rays could see inside the body. Why not look? They found nothing. Other experiments tried weighing people at the exact moment of death to see if something departed, if the body became lighter when the soul left. Results were inconclusive at best, but here's where quantum consciousness offers a tantalizing, if entirely speculative, possibility. If consciousness is quantum in nature, if it's sustained by quantum processes that aren't confined to the physical brain, if quantum effects connect us to something beyond our immediate biological structure, then there's at least a theoretical case that consciousness could extend beyond physical death, perhaps existing in another form, another dimension, sustained by quantum information that doesn't simply vanish when neurons stop firing. It's the most hopeful case anyone can make for continuation after death. But it remains entirely unproven. And the only way to find out with certainty is one nobody volunteers for. And here's perhaps the most beautiful mystery of all. There are monks who walk for peace, from Texas to Washington, D.C., walking constantly, day after day, and observers report something remarkable. As they walk, they begin to seem like one entity. Their steps synchronize, their pace aligns, their breathing matches. They move as if they were a single organism rather than separate individuals. Are we all, in some deep way, one being? Physically, no. They're separate organisms with separate nervous systems, but what they achieve is extraordinary synchronization. They communicate through sight, sound, rhythm, shared intention. They listen, they watch, they align. This isn't unique to monks. Soldiers marching in formation experience it. So do choir singers harmonizing together, each voice blending into something larger than any individual. Athletes on championship teams describe it, a flow state where the team moves as one mind. We humans walked out of Africa and spread across the entire planet on foot, through Europe, Asia, across the Bering Strait, down through the Americas. Walking together is written into our genes. Synchronizing with others is wired into our nature. Some people experience this connectedness at even deeper levels, through meditation, through spiritual practice, through altered states. The feeling of oneness, not just with people nearby, but with all humanity, with the planet, with the cosmos itself. Everything connected, everything part of one fabric. Whether this reflects something physically real, some quantum entanglement between conscious minds, some shared field of awareness we haven't discovered, or whether it's a profound subjective experience generated by our remarkable brains, we don't yet know, but the experience itself is real. It's been reported across cultures, across centuries, across every spiritual tradition on Earth, and it hints at something beautiful about what it means to be human. So where does all of this leave us? We live in a universe that is 95% mysterious. We have two magnificent theories of physics that cannot communicate with each other. We don't know whether time is still being written or already complete. We can't explain how entangled particles coordinate instantaneously across the cosmos. We cannot define consciousness, let alone explain how it arises or where it goes. The possibility of uploading minds may be fundamentally forbidden by physics. And the question of what happens after death remains exactly as unanswered as it was when the first human looked up at the stars and wondered. And yet, this is precisely what makes science the most extraordinary human endeavor ever conceived. Because science doesn't pretend to have all the answers. It begins with the most powerful words any curious mind can speak. I don't know. And then it goes looking. It asks questions. It tests ideas. It fails, learns, adjusts, and tries again. Every unanswered question is not a defeat, but an invitation, an open door, a frontier waiting to be explored. We are, each of us, standing at the edge of the known, looking out across a vast ocean of mystery, and the only way forward is curiosity, the willingness to admit what we don't know, the courage to keep asking questions, keep looking up, and never, ever stop being curious.